right, good morning, everybody. We're going to pick up roughly where we left off last time, which is thinking about the idea of a hash table. So let's review a lot of what we went over, what we learned about last time, and then we're going to spend some time today thinking about details of the implementation, a couple of different approaches, and we're going to think more about what we have to do to put together a good hash function. So the idea of a hash table is to try to create an array with an arbitrary index, not just ints. So arrays are a great data structure for what we call random access. That is constant time, add and delete, right? But they're very restricted in that the indexes can only be integers. And that comes about because of the very nature of the reality of an array. The nature of an array is to be a slice of consecutive memory locations in RAM. And so we use the array index as an offset on the memory address of where the array starts. But there is a lot of value in being able to have an array with an arbitrary index, and that's where hash tables come in. So the key idea, the key insight of the hash table are interconnected. So the first key insight is the idea of a hash function. And much as I did on Friday, I will be discussing the hash function assuming that the thing being hashed is a string. That is both for illustrative purposes. It is also because it's honestly the most common thing that gets hashed. That said, you can hash anything for which you can define a function that maps it to the integers. It can apply to any data structure, not just strings. But we'll just be working in terms of strings as kind of a convenience for the exposition. So you have a hash function that takes some string and then returns an integer. And then once we get this integer back, we have to normalize to the table size. Normalize to the table size. Anyone remember the technique we discussed last time for normalizing our integer output of our hash function to the size of the table? What amazing arithmetic operator enables us to do this? Mod, yeah. There are other ways to do it, but mod is absolutely the most straightforward. So easiest way to normalize to the table size is to use mod. So you've got some function that takes your string, turns it into an integer. Now a hazard here is that many different strings that are distinct might still have the same corresponding integer value. And so the other big idea with hash tables is that we have to deal with collisions. And a technique we discussed for dealing with collisions last time is known as chaining. And so this is a really straightforward idea. You've got your hash table, and each entry consists of a linked list. And so whenever you add something, it becomes a node in the linked list. But if something else arrives that has the same hash code, we just make our linked list a little longer. Now, this interaction between the hash function and the phenomenon of collisions means that we need to think very, very carefully about the hash function. today and this week, I'm just going to be giving you a fairly superficial introduction to hash functions. Good hash functions is a deep, deep topic.
It's like a rabbit hole.
You can spend a lot of time thinking about hash functions, yes. There are a lot of sophisticated ideas behind what makes a good hash function. We're going to be looking at kind of the simpler ideas today and this week. And time permitting and attention permitting, we might look at a little bit of the deeper issues as well. But the fundamental idea is that this hash has to produce values that are uniformly dispersed. We need our hash function to hit as many different cells in our table as possible, given the information encoded in the inputs that it receives. So, the end of class last time, we talked about a possible hash function for strings. What was that hash function? Anybody remember? What was the hash function we looked at for strings last time? If nobody remembers, let's see if we can reconstruct it. So, to turn a string into an integer, we think about what a string is. And a string is just an array of characters. Now, each character, in turn, is really just an int that encodes that symbol. For instance, 65 would be capital A, 66 would be capital B, and so forth. So this array of characters is really just an array of integers. So what is a very simple way we can convert an array of integers into a single integer? Very simple way. So again, thinking about this in some more detail, if I have two integers, x and y, and I want to convert them into a single integer, how can I combine them? Add them, yeah, that's right. And so similarly, I can add all of the integer values in an array, and that gets me some single integer as the output. And so this is an example of a simple hash function that takes a string and converts it to an integer. So we looked at this last time, and it had a fatal flaw. And we got to this at the very end of class. Does anybody remember the fatal flaw in this scheme?
Because like palindromes.
Anagrams.
Anagrams have the same value.
Right. The flaw is that anagrams share values. So if there is an ant that gets a tan, it turns out these hash to the same value, but they're very different words and they're very different concepts, ideally. So what we need is to think about how can we take this underlying idea of combining these values with a single operation in a way that gives different anagrams with the same letters different values. So that is the challenge I am posing for you all this morning. So let's do this. I'm going to break you all up into 3 groups. We'll have Paxton and Morgan chat, Jake and E-Ray, and the 3 of you there. And I want each group to take a couple minutes to brainstorm and figure out what can we do with this hash function so that it does different things with different anagrams of the same letters. So chat, brainstorm, let's see what you come up with.
My thought would be to add one, but I doubt that's the case. Because adding one would change the value, you can probably change one of the letters even though it's straight.
Yeah. If you add one, you add the numbers, it's going to change which letter it is. So that's going to be there. So you can-
Yeah, that's why I said it's probably not possible.
All right. So. We distinguish about altering at least without altering it so that it's irreparably changed.
I'm trying to think.
Next is complete, just square each one.
I would say change the order of values maybe. They record the order.
Yeah. Might work.
That's my idea, but I'm not exactly.
Well, you can always test your idea. Make a simple example and do the idea.
Well, the idea is that we're going to record the order of the of what went in.
So that sounds really vague. So you need to make it more specific. Well, what are you going to do with the order? How are you going to record it? What's the recording going to look like?
Well, I mean, you said we can put arrays into an array, correct? Well, wait, that's a dumb answer. Why did I ask that? I'm trying to think about this and
You all come up with anything?
We were thinking about rather the exponent and plus one or multiplying by plus one for each individual.
Hang on to that idea.
Yes, I did. And you could either yeah.
Okay, so I think there are a couple interesting ideas running around. Let's try them out. So, Elijah, what was the idea your group came up with?
For whichever position it's in the word, either add that. So if it's like the first letter, either add or multiply it by that number.
Okay, so let's formalize this with an example and get a feel for how it might work. So I have ant and I have tan. And so here we have these positions. So for each of these, Elijah, walk me through the process of turning it into a number. And to keep things simple, we're going to say that A equals 0 and Z equals 25. So we're going to turn these into full-blown integers. We're going to do the whole calculation. So what's this look like? Okay. Oh no, he got his fingers out. Plus 13, okay. Okay, and so ant adds up to 32. What about tan? Walk us through tan.
Would be 0 plus 16.
Mm-hmm.
And then
And then 2 plus what? 17. Oh, it was a noble attempt. And I think there's a core of a great idea in here. And the core of the great idea is that we must somehow mathematically incorporate the position. But I heard you say something like that, didn't I? That maybe multiply them? Okay, so let's try that instead. So if we take your basic approach, and instead of adding that index, we multiply by, let's just see what we get. Okay? So we would get 0 times 0 plus 1 times 13 plus 2 times 16. And that would get us 32 plus 13 is 45. And now if we come over here, we get 0 times 16 plus 1 times 0 plus 2 times 13. And that's 26. And these actually differ from each other. So this is a possible candidate. We can consider this. All right. Jake and Ire, what did you all come up with?
We were thinking doing multiplying each one by n plus 1.
Multiply each one by n plus 1?
Yeah.
So it would be similar to this scheme, but one higher?
Yeah.
Okay.
Or doing an exponent. Or multiplying. So it would be, I guess, 0 to the 1 and then 0 to the 2.
Oh, I got
13
you.
to the 2 and 16.
Okay, so this is a very interesting approach. Let's walk through it. So you're saying 0 to the first, so the value to the n plus 1
Yeah.
of the index, plus 13 squared, plus 16 cubed. All right, so let's add it up. 0 to the first is 0. 13 squared is 169, and 16 cubed, give me a second, is 4,096. So let's add these up. So 9 and 6 is 15. What do you know? We're adding 9 and 6 again, but with a 1. 16, 2, 4. So 4,265. Okay. So now let's look over here. We have 16 to the first plus 1 squared. No, 0 squared. Whoops. Plus 13 cubed. So that's going to be 16 plus 0 plus, oh, this one's fun. Let's see.
Can I just pull out a calculator?
Sure.
Just for the sake of it. And
Go for it. Let's see how we do. So we have 160.
2,100 and 2,197.
Is that right? Nah, that can't be right. Okay. All right. So in any event, yeah, we got 2197 plus 16 is 22. 13. So that's good. These are different. So we've got two viable hash functions here that address the problem of anagrams. So good work. Good work. Now, though, let's pose the question, which one of these is preferable in general, might you think, in terms of minimizing collisions? Why?
I think it's just easier to put the values, and then instead of having values that are in the thousands.
I think, yeah, I agree with him. Having values that are less than thousands will probably limit it.
So if you have smaller values, you expect fewer collisions.
Actually, no. It should be larger. It should be larger by the sake of there could always be a case where we would run into another case of say 45. In that.
Right. I think you're capturing a nice intuition there, Morgan. We're probably going to prefer this approach because it's going to spread values out a lot. By analogy, so first, I want to show you all something. So let's do a little Google search, Java 11 string hash code, and we're going to go to the Java 11 docs, and we're going to see their description of what they coded for Java's string hash code. All right, so here it is. Whoops, I just scrolled past it. Oh, now I made it bigger and lost it again. Just a second. There we go. Can everybody see this in the back row? Is that readable?
Yeah, that's readable.
Back row. Okay. So, returns a hash code for this string. The hash code for a string object is computed as s bracket 0 times 31 to the n minus 1 plus s bracket 1 times 31 to the n minus 2 all the way down to s of n minus 1. This isn't exactly what Jay and E-Ray came up with, but it's really similar. So the way you can think about this is that it is interpreting the string object as if it were a base 31 integer. So let me show you what I mean by that. That might have sounded a little cryptic. Let's think about what we mean by place value in terms of an integer. So if I talk about a number like, let's just borrow a number, 4265, right? You can think of this sequence of digits as being an array. And each cell of the array has a particular constant multiplier as follows. You have 5 times 10 to the 0, 6 times 10 to the first, 2 times 10 to the second, and 4 times 10 to the third. So what we have is place value. But of course, 10 isn't the only possible base. It's just the one that we tend to use most routinely. If we go with base 2, for example, well, what's this really mean? This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, right? And so I can look at this, and in base 10, this is just 13. 1 times 2 cubed, which is 8. 1 times 2 squared, which is 4. 8 plus 4 is 12. 0 times 2 to the first. And then 1 times 2 to the 0, which is just 1, right? So what we are seeing here then is each integer value corresponding to the given character is being multiplied by this number 31 raised to a given power. And that number 31 is initially raised to the power of n minus 1, as if we're in the leftmost place of a place value. And then we add 31 to the power of n minus 2, the next place over of place value, and so forth. And I really, really wanted to show you this because I think there's a lot of value in understanding what a commercial grade language like Java actually does for its hash function.
Does Python have a hash function?
Yes, Python dictionaries are hash tables.
Oh, is that what they are?
Yeah,
Huh.
yes. Python dictionaries are hash tables.
So wait, we can make a dictionary using a hash table.
Yes, so if you code up a hash table in Java, it will be a dictionary. You don't actually have to do that in practice. I mean, you'll certainly be doing it tomorrow. Make no mistake. You're going to be...
Isn't tomorrow the last lab?
It is the last sort of structured lab. lab won't meet next week because it's Thanksgiving week. The following week, the last week of classes, the lab period will meet, but it's going to be solely time to work on your final project.
Okay.
So yeah, but tomorrow is the last sort of formal lab, and this is the final data structure we're studying this semester.
Okay.
Yeah. So so tomorrow you're certainly going to be coding up hash tables. But yeah, this is what widely used commercial grade language implementation has in its standard library for a string hash function. So it wasn't hugely far off from what Jake and Ire were
Why
talking about.
31 base power?
Well, let's think about it. Why do you all think it's treating it as a base 31 number?
Well, I've heard that. Well, there's one good example is like 30 simple to Windows kind of thing. It's kind of like 32 bits.
32 bits has a lot to do with it. Like a huge amount to do with it.
So I'm guessing is each number a bit maybe, or each letter a bit?
It's not so much that each letter is a bit as it is that each letter is encoded by up to 32 bits. So let's review a little bit what we talked about last time about Unicode. So Unicode is a character encoding where every letter in every writing system has a 4-byte encoding. And so 4-byte is 32 bits. And so what's really cool about this is it gives us all the space we need, right? So 2 to the 32 is about equal to 4 billion. Notice I wrote an equal sign and then I didn't really want to spell out the precise value. So
Could you? I'm just getting the last of this.
yeah. So what we have then with this idea of treating a string as a base 31 number is acknowledging, we're not actually using the full 32-bit range, but we're getting fairly close. By using the 31-bit range, what we're saying is it's like every letter is its own digit. When we have a base 10 number, we need 10 distinct digits. When we have a base 2 number, we only need 2 distinct digits, 0 and 1. Base 31, we would want we can handle up to 31 distinct, or 2 to the 31 distinct digits. Now, there aren't really that many. And that's fine, but it can accommodate them, especially if somebody invents yet another pictographic language with 100,000 characters or whatever, like Chinese. Yeah.
Hey, we write something in Wingdings.
Yeah.
How often is Unicode updated?
I mean, it's pretty set,
Okay.
right? So we can actually go to the Unicode website. Yeah, Unicode, the world's, so at this point, every emoji has a Unicode encoding. So
Hold on. Wingdings, anyone?
what is a wingding?
Wingding it's more symbols than letters, but it is a writing.
So this Wikipedia page has a list of Unicode characters. So as a version 12.1, it contains 137,000 characters covering 150 modern historic scripts. So this just gives a subset of important ones. So yeah.
No, I'm sorry.
Yeah. So, here's Latin uppercase, Latin lowercase, the Latin supplement. It's got stuff like pound sign, yen sign, and so forth. We've got variations with little tildes and other symbols on them, and so forth. And this is just still in Latin extended. And so this is covering most European things. And there's Latin extended B.
How much is it? Latin?
there's a lot of things you can do with Latin letters. But then eventually we get down somewhere in here. Yeah, we get to Greek. We get to Cyrillic, which is, yeah, it's the alphabet used for many Eastern European languages like Russian. Yeah.
Russia would be fun.
What's that?
Russia would be fun. They have a lot of symbols too.
Oh, yeah. Armenian has its own block. Armenian has a unique alphabet that looks like this. It's just their alphabet. It's, and then there's the Semitic supplements. You've got Arabic, Mandaic, Samaritan, Syriac, Hebrew. Then there's like all the different character scripts from India. So that includes all of these.
Wait, is there a legitimate list of question? Could we actually write something in Unicode into Python into Java using Unicode?
Oh yeah. All Java strings are Unicode strings. Now, your computer might not have the fonts to support them. So not every computer comes in with font support for every Unicode
But
character.
it can be installed.
Absolutely, yeah.
When, I know there's like, I think you can press Alt and then like hit the number pad to make symbols pop up. Is that like typing in their Unicode?
That's often the way it's done, yeah. Yeah, so then there's other Asian systems, Georgian,
What?
yeah,
What is that?
from Georgia.
Wait,
Not the state, the country, the nation, in the Caucasus Mountains, former Soviet Republic of Georgia. Yeah.
Okay, somewhere near Russia, basically.
Yeah, then there's some African scripts. Cherokee, of course, is a very famous script from the Cherokee Native American language. Mongolian. I mean, it just keeps going on and on. If you can load a font, you can represent it as a string in either Java or in Python 3. This is actually a major difference between Python 2 and Python 3, is that Python 3 went to Unicode strings. But yeah, most modern major programming languages support Unicode now.
Python?
That's what I just said, yes.
I'm sorry,
Yeah.
my brain just shut off.
Okay. So that's pretty cool. This is a really effective way to encode stuff. But now we need to kind of get into the nitty gritty of how these hash tables are implemented, right? We know that we need certain ingredients, right? We need a hash function, and we need an array. And each element of that array is going to be a linked list. Well, it doesn't absolutely have to be a linked list. This could, in fact, just be another array. The reason that we typically use a linked list here is to facilitate deletion, basically. Although they don't tend to be all that big, and you still have to iterate through the linked list to find it. So, yeah, you could probably just use an array there just fine, now that I think about it. So,
Isn't the simplest way to use an array just clear?
well, but you don't want to clear everything in that cell,
Oh, no, no.
right?
Well, no, in that specific array, in that cell.
Right, but then you have to move everything down to cover it up. That's the disadvantage of an array.
No, never mind. I was
Yeah.
thinking of something else. All right.
So structurally then, it looks kind of like this. And we've got our lists of items hanging out there. And so there are a number of considerations when actually turning this into code. At a certain basic level, it's of course very, very straightforward, right? You have an array. Its elements are either linked list nodes or potentially array lists. You can make it work either way. But there are some subtleties. The first subtlety is figuring out when you resize. So unlike a resizable array where you're forced to resize when you've occupied every cell, in the case of a hash table, or a chain hash table specifically, in principle, you never have to resize, right? Because you could simply allow each of your buckets to just kind of get fatter and fatter and fatter. But I think we are going to want to resize periodically. And the reason we want to resize periodically is that we want to limit the average length of one of these chains to be a constant. So in order to do this, we calculate what's called the load factor of the hash table. So as we're implementing a hash table, it needs to be aware of its own load factor. And by being aware of its own load factor, it can make what we'll call, for lack of a better term, an intelligent decision about when to resize. So this load factor is very, very easy to calculate. You just take the number of items stored and divide it by the number of array cells. And that gives you your load factor. So actually, let's go back to the documentation. This will be fun. If we go back to, so actually we're going to go to the hash map class. So Java 11 hash map. So hash map is the primary hash table implementation provided in the standard library. So here we go. And it says it right here in the documentation. As a general rule, the default load factor 0.75 offers a good trade-off between time and space costs. So this is what, again, in kind of a commercial grade hash map, the load factor that's actually used. Higher values decrease the space overhead but increase the lookup cost. So in other words, let's say I allow a load factor of 3. Let's look back at how I defined it. A load factor of 3 means the number of items, I'd have 3 times as many items stored as array cells. So my average bucket is going to contain 3 values. So in light of that idea, what they're explaining here in the documentation is that decreases the space overhead, but it increases the lookup cost. Why does it increase the lookup cost? Because on average, I'm going to be searching 3 items before I find what I'm looking for. And then a lower value, of course, increases the space overhead. If I've got a value like 0.25, I'm demanding 3 empty array cells for every single item I'm storing. So it's a trade-off. There's no perfect answer to this, but I think it's worth seeing what's done in a commercial grade implementation. And so Java uses 0.75, for example. And so you'll have to do the same thing. As you create your own hash table, you always need to be tracking your load factor. Obviously, the denominator is really easy to calculate because you can just check the length of your array. The numerator requires maintaining a size instance variable. And it's important to maintain this as an instance variable because you don't want to have to iterate all the way through your hash table to find out how many items are in it to calculate the load factor, which you must calculate on every insertion into the table. And the reason you have to calculate it on every table insertion is that the moment you go above the load factor, you have to rehash. So what do we mean by rehash? This is like resizing, but with a hash table. Because we're using a hash table, there's a really subtle difference. And that really subtle difference comes about from the fact that way back here, we used mod to normalize to the table size. If I resize my table, many of my elements are going to need new homes because I am now not modding their hash code by the old size, I'm modding it by the new size. So they're going to need to go to new places. So when I rehash, I need to visit every value in my old table and do a brand new insert into my new table. And so something that's just hugely important about this is that there are likely to be fewer collisions when you rehash. Because you're now taking the modulo relative to a larger table size, lots of values that were sharing space before and bumping into each other and not having enough elbow room are actually going to wind up in completely different locations. So when you do the rehashing, it's often easier to create your new array and then have a reference to your old array hanging around, and then immediately update your table to point at the new one, and then just call your insert method over and over again and let it do all the hard work of building out the chains. That is far and away an easier approach to the implementation. And so, yeah, rehashing is something that we do whenever we exceed our targeted load factor. So the initial hash table doesn't really need to be very big because you're going to rehash whenever it gets too big. And it's actually pretty reasonable to start with a fairly small size of the hash table. The reason for that being, once you have created a library that has a hash table data structure, people are going to use it for all kinds of stuff, even data sets that aren't very big, because it's a much more natural abstraction than an array for those kinds of tasks. If I've got a name that needs to be associated with some value, I should instinctively go for a hash table. In practice, the hash table turns out to be one of the most important data structures ever invented. On a practical level, it tends to do even better than a trie. Not that the trie does, yes?
No.
Okay.
Sorry, I was there.
Not that the trie doesn't have the potential to do just as well, but the reason the hash table does better than the trie in practice comes back to the memory hierarchy issues I was discussing last week. That is, with a trie, I have to have these separate nodes for every distinct letter that I'm storing. And because these nodes are not consecutive, I tend to have, whoops, I can't spell. Let's try that again. I tend to have cache misses with them. On the other hand, with a hash table, it's built on the nice cache-friendly structure of an array. So with a trie, if I'm looking up a word like hello, I might have 4 or 5 cache misses before I get in there. With the hash table, especially if I use arrays in my buckets, I'm just looking at 1 cache miss. So I've personally done some experiments on this, and I found that if I coded up a hash table, and the hash table I coded up runs roughly as fast as the Java library one. So if I code up a hash table, it runs about 3 times faster than if I hand code up a trie. Now, a trie is arguably more elegant, a little less cognitive burden because you don't have to even worry about hashing and collisions and all of that. The trie kind of gives you better guarantees about what's going to happen. But much like quicksort tends to run faster in practice than the nice, elegant merge sort, Hash tables tend to run faster in practice than the admittedly more elegant trie. Sometimes life just isn't fair. There is a cognitive load with the idea of hashing, but in general, they work pretty well. So that's why in Python, the dictionary, that main workhorse data structure of Python, is just a hash table underneath. And the hash map is one of the most heavily used data structures in the Java language as well. In a way, the hash table winds up seeming as if it's the perfect solution to the problem of searching and storing, right? Why? Because you get, so let's think about how we reason about performance, right? If we think again about how we reason about it in terms of the trie, we had D, the depth. We had B, the branching factor, right? Well, with a hash table, you don't even have to think about B. Hash table will give you expected case O of D for insert and remove. This is really terrific, especially because N is nowhere to be found. Yeah, you have to rehash from time to time, but that gets amortized as it did with the array list, and in practice, these tend to work pretty well. I think you'll find, just as hopefully you found in Python, you eventually found yourself using dictionaries everywhere. In Java, you would find yourself using hash maps everywhere. I certainly use them all the time. Of course, it's not totally perfect. Iterating is not a pretty story, because not only are you not guaranteed for them to be sorted or anything, you're not even guaranteed to get order of insertion. Because when you add things to the hash table, they can wind up literally anywhere in the table. So if you need a certain preserved order of insertion, you wind up needing to augment the hash table with another data structure. So there'll even be combo hash table linked lists that keep every node in a nice big long linked list so that you can iterate through them in the order of insertion. And if you really need it sorted, of course, at that point, you need a trie or a binary search tree. In fact, this idea of preserving that order is so incredibly common that the standard Java library has this great data structure called linked hash map. And linked hash map is just like hash map, except when you use a for loop to visit everything in it, you get it in insertion order. And so if having a stable order matters, then you wind up needing the linked hash map. Sometimes in projects, I wind up transitioning a lot. So I'll maybe start something with a hash map, then I iterate over it, and I might switch to linked hash map. And then I don't like the ordering. I want it sorted, and then I'll be switching to a tree map, which is the Java balanced binary search tree. And yeah, they all use the same methods, and so you can kind of swap between them in your code as you need to. So these are the basics then of not just hash tables, but specifically what's called, let me write these names down. What I've gone over is known as chained hashing. It's also called bucket hashing. There are others, and we're going to look at some of those others over the course of this week. There is open addressing, and my personal all-time favorite, which is cuckoo hashing. And we'll talk about that as well. Yeah, cuckoo hashing is a great algorithm. All right, any last questions?
Question, can you assign a random, so say you have like a name, you want a dictionary, a hash table to have a name tied to it.
Okay.
So you have a name and an age tied to it.
Okay.
Could it be possible to have a hash table to assign names?
I mean, you could store the name as key and the age as value, certainly.
Okay,
Yeah, I mean, that's a good use of a hash table.
okay, because that's what I remember from dictionaries, having the capability of having a key in it.
Yeah. Yep, that's a major